Thank
Wonderful.
you.
Thank you, everyone. It's nice to be here. Okay, I think people are settling in. Okay, I can start. So, my name is Nikhil Barthwal. I'll be talking about evolutionary architecture. How do you build systems that can evolve over time? And the agenda I have for today, I don't know. Okay, good. Maybe the arrow keys are not working. Never mind. So I'll start by explaining what evolutionary architecture is, why do you need it, sort of problem definition. Then we introduce some architectural principles like cohesion, loose coupling, connaissance. These are more or less, people are sort of familiar with it. It's just a fancy name to something we already kind of know very well. And then we talk about various architecture patterns that we use in evolutionary architecture. We go about that we have these different components, what kind of communication patterns we can use across them. We talk a little bit about Conway's law. I'll explain what Conway's law is and how it influences the architecture. Then we talk a little bit about data. In fact, I would say data is often more important than the architecture itself because data usually outlives the application. So we absolutely want to cover some aspects of data. And then I have sort of best practices across governance model, feature selection, technology choices, etc., of how we can support or do evolutionary architecture. So let's start with the problem definition. Okay, so we all understand what a software architecture is. Basically, it's a blueprint that you want to build a building. Architect draws it on the paper. You want to build a software. You understand what the problem is. It's a blueprint for future implementation. Sounds about good, but there is a small catch here. That when we build an architecture, we assume something about the future, but in reality, future is far more uncertain, right? So when you're building an architecture, you're trying to solve a problem. You think you understand the problem, but the world changes way too fast, especially with all this AI stuff going on. Requirements keep evolving in a way that you cannot predict. So it's very hard for you to basically predict the architecture. Some of the early assumptions that you make often prove wrong. So there is a common myth around that we know the stuff, we build it, and then we just build the system using those blueprints and we start implementing. But once you hard code an architecture and you start building on it, it's actually very difficult to go back and refactor the problem. So that's where evolutionary architecture basically comes in. Essentially, it's bringing agile philosophy to architecture. I'll talk about it. But I'll explain like the software decay. So what a software decay here is that you have a base architecture, right? Once you have established, it's very hard to change. And this leads to what is called a software rot, software decay. There are different definitions for the same problem. So you have a slow deterioration of software quality that in the beginning it's very less, but as time passes by, it grows. And often software becomes very faulty, but at that point, it's very hard for you to go back and re-architect. Basically, you're now doing re-implementation of pretty much everything. So evolutionary architecture is basically a design approach that is used to solve this problem. The fundamental assumption about evolutionary architecture is that treat architecture as an evolvable entity. It doesn't really have an end state, but it's just designed to keep changing. So essentially what you're saying is that I have a system, here's an architecture, but I do not know if this is the final architecture. This is like the base architecture, and as time passes by, this architecture will evolve to enable new use cases that we haven't thought about before. So like I said before, it's kind of agile philosophy where our architecture is essentially optimized that it can be changed. Now, how it's done in practice, I'll cover throughout the talk, but that's the core idea of evolutionary architecture. Like your architecture, optimize your architecture for change. Do not make an assumption that once I've architected the system, I understand the problem, I can just build on this architecture. So how you actually practically do it is that when you have an architecture, you first need a mechanism to evaluate how good an architecture is. So you define some kind of characteristics. We'll have some examples of characteristics across multiple dimensions. These are my desired feature. And then what you do is you define a fitness function, which is sometimes empirical, sometimes it's analytical, but some way of evolving. Because you have an architecture, you should be able to quantify how good that architecture is. Ideally, you should be able to assign a score between, say, 0 to 10 or something like, this is how good I'm doing. Because if you don't really have a measure of defining how good your architecture is, you really don't know what you're doing. And then, as an agile approach, you basically start making changes to that architecture. As new requirements come in, new use cases are discovered, you kind of make an architecture, you're guided by the fitness function, which is essentially guiding you on the direction to take. And you evaluate it across all dimensions. Now, I keep saying dimensions, architectural dimensions, but what are these dimensions that I'm talking about? So here are a couple of examples of dimensions. So you're talking about audibility, right? Especially in healthcare where I work, auditable is really good. Even finance, auditable is very good. You often have some performance characteristics, right? I define my architecture, I'm trying to do some services, I have an SLA that I need to meet. So if my SLAs are not being met, then I know I have a problem. Now, this is a little bit tricky because sometimes performance is defined in terms of a combination of hard and soft constraints. Hard constraints that I need to meet, soft constraints that are desirable properties that ideally I should, but in real life, we almost always, like all engineering principles, you have to make some kind of compromise. So this is where it's coming back and saying that fitness function gives you, basically tells you how good your architecture is, but understand that evaluating an architecture is more of an art than a science. It's not always that you can have a proper analytical function. Sometimes it's a little bit more empirical. Security obviously is very paramount, especially if you are in certain situations like finance, etc. You want to have proper security. Then data. Data is absolutely important. Data protection, data governance, GDPR, privacy regulations, all sorts of things we are talking about here. Then legal and compliance. Nobody wants to get into legal troubles. We also have scalability. We make money because our services are scalable. So these are the these are some of the examples of architecture dimensions. Of course, depending on the problem you're solving, there could be others that I have not covered. And like I mentioned before, we are talking about evolutionary architecture as some form of agile approach applied to architecture. So I built something, series of small experiments. I build, I guide, change my architecture, make like guided incremental changes in form of small deltas, whether I'm doing it in like sprints or doesn't really matter what method you do. And then you measure, you understand like how good my architecture is, you learn from it, and you take it in the next cycle. Another thing about evolutionary architecture, in fact, it is true for agile, is that agile systems or evolutionary architecture, as one example of agile system, is a mindset. It's not a process that you have to have sprints and then you become agile. You don't really have to adopt a process. It's just you have to change your thinking. You become agile. Like some people have this notion that if I'm doing sprints, then it means I'm agile. Well, you might be doing sprints, that doesn't necessarily mean you're agile. And even if you're not doing 2 weeks, 1 week sprints, etc., then it doesn't always mean that you're always agile, because it's about mindset. The whole mindset is that agile is about failing fast. It's about changing directions fast and adapting to the outside world. That's what agile is. That's the agile in software development. Evolutionary architecture is the same agile in software architecture field. So we start by talking about one of the principles of connaissance or coupling, whatever you like to call it. And in some form or other, it's actually very well known. But essentially, what we are really saying is that two components are connaissant if a change in one is required, it would require a change in another one. So this is also called coupling, right? So these components are coupling, and there is two kinds of coupling. There is one which is called static coupling. We'll have some examples of static coupling, but that's like source level coupling. And then there is an execution level coupling, which is actually even worse than static. And this is kind of examples of static and dynamic. So for example, when you are dependent on timing, it's an execution because it can give you issues like race conditions and all those things. When you're using a particular algorithm, and let's say if you change the algorithm of one component and you are required to make changes on another one, that's static coupling. They're both coupling, but generally dynamic coupling, ideally you want to avoid coupling. in all forms. But in real life, that's always not going to happen. Sometimes you need to have coupling, some level of coupling. So ideally, you want to minimize the coupling. And what you want to do is wherever you can replace dynamic coupling with static coupling, you want to do that. So that's what the principle of connaissance or coupling does, and we'll see how it plays out. So cohesion is another kind of principle. We have used it in object-oriented programming, but essentially what we are saying is that any software component, any software, we basically have set of modularization, whether you're using object-oriented programming, you have classes, etc. It doesn't really matter how you basically do this component-based software engineering, but essentially your software consists of components that you're grouping together in form of module. And what you want to do is all related things should be in one module. You don't want one, like say you're handling some financial, so you want some account stuff, all the related things to account should be in one module. You don't want elements of account to be spread across module. So here is a diagram, okay? And ideally how you do it is that within a module there is often close-knit dependency, so high degree of graphs, but inter-module, you essentially have less dependency. So that's why you're seeing this more of blue lines and less of green lines in the diagram. And there's an inverse relationship between cohesion and low coupling. Higher your cohesion, lower is the low coupling. In fact, principle of cohesion is very much followed in object-oriented programming, because when you really understand what the basic of object-oriented programming is, object-oriented programming says that you have basically some kind of data, which is your private data, and all the things you can do to this object, this collection of data, you define methods to it. So object-oriented programming is basically saying, and the design principle in object-oriented programming is that anything related to data should be put in one class. That's a principle of cohesion. When you're doing microservices architecture, you have the same thing. All related things should be in one service, and services should call each other in form of loose coupling. We'll talk about microservice architecture a little later on, because microservice architecture is one of the ways we follow, one of the practical ways we do evolutionary architecture, not the only one though. So you have low coupling. When you have the opposite, where you don't really have a lot of interdependent ones in one module, you have basically tight coupling. That's the situation you actually want to avoid, because software is often read far more times than it's written. And if you have a situation like this, it's actually very hard for anyone to understand what is happening here. Right? You want your software to be readable. In fact, when I write code, my number one criteria is this readable? Is this maintainable? That's far more important than how clever and smart the algorithm is. That's probably not going to make that much difference. But maintenance is going to be the single biggest issue. The cost of a software is really a cost of maintenance. We'll talk a little bit about domain-driven design. Domain-driven design is a big topic, and I only would cover very little of it and how it's related to evolutionary architecture. But in simple words, that's the textbook definition of domain-driven design. What domain-driven design is that you basically think of your software as a model, and you connect your implementation to an evolvable model. So let's say you're designing something from banks, so you have a domain of finance, you have different components like bank accounts, transactions, users, customers. It's a model. And there are different entities like bounded complex entities, value objects, which are basically value types, aggregates, things in which you are grouping together, services, and then you have bounded context. Bounded context, which we'll talk a little more, is essentially that in real life, a software is very complicated, so often you can't represent it as one model, but it's a set of models interconnected with each other. I have some references for domain-driven design. Eric Evans is basically the original person for DDD, some practical advice. Like I said, I can't go in details because there are conferences just designed for domain-driven designs. But we'll cover a little bit about bounded context, because from an evolutionary architecture point of view, this is the stuff that is important. So a bounded context, here is a diagram that I picked up from Martin Fowler's website. So bounded context, we basically have different models connected together. So there's a sales context, there's a support context, and you can think of any model in real life as collection of different submodels related to each other. And note that this is sort of tied to the same cohesion tight coupling that we are talking about. So it's the same idea that in a different way is formed in domain-driven design, where you can think of a bounded context as basically some kind of model or submodel within which you have high cohesion components and interconnected, and there are less cohesion between different models. So that's what domain model and bounded context would say. And the reason why bounded context is important from an evolutionary architecture point of view is bounded context is basically going to give you boundaries for partitioning. Because when you think about complex system, one of the challenges that you face is that, okay, I understand that there is this, but how do I partition it into modules? How do I basically separate it? And bounded context is basically giving you these are the boundaries. Now, I should point out that there is no unique way of separating a software into different components because you want modularity. Sometimes, for example, you could have something like customer as one module, producer as another module, transactions as third one. Sometimes you might combine customer and producer as one module. It's more of an art than a science. In fact, in microservice architecture, we have this problem of how do you divide the functionality into different services, right? And again, there is no unique way of doing it. You start with your initial guess, and as your system evolves, what you might do is you might combine microservices, you might split microservices if they become too big. So DDD kind of does the same thing, right? You start with an initial, and then you evolve the system as time grows. So another architecture pattern that we'll talk about is layered architecture. It's very common here. And essentially, loosely, you can think of it that your software has 4 different layers. Although in real life, it has several layers, so I should rather say something like 4 types of layers. Maybe, because in a very complex system, you might have multiple business layers, multiple persistence layers, etc., etc. But there's a database, right? There's a persistence. There are just value objects that are being held here. There's a business layer, which is basically transactions that are happening. And then there's a presentation layer, which is often for web software, it's kind of a UI, it runs on the browser. But essentially, your software consists of layers. And each layer is an abstraction that provides clear boundaries of how these layers can interact with each other. So layered architecture is one form of evolutionary architecture that you divide your software in layers. But the only thing is sometimes you can run into cases where there are certain issues that cuts across multiple layers. For example, certain error edge cases like error handling, etc. So you have to be a little bit cautious about it. Another thing you could do for evolutionary architecture is what to call as modular monolith. Modular monolith says that in a typical monolith, you have all your services in your functionality in one services, right? Modular monolith, that's okay. You can have all your functionality in one service. But within one service, what you have is you essentially have modules, and the modules will have clean interface. So it's an architecture where you divide your logic into modules and let modules be independent and isolated. They have their own schema, and they can talk to each other. They are still part of the same service, though. It's just a logical separation within the service. In fact, in some sense, you can think of modular monolith as the opposite of microservices. Microservices says that you have these functionalities into different services talking to each other in common web protocols. Modular says you can have it in the same one, but you can have it in the same service, but within the same service, the code is modularized. So I've already kind of explained microservices architecture, but microservices are very common. It's basically autonomous services that work together, approaching set of small services, communicates with common protocols and lightweight mechanism, assembly of loosely coupled services. In fact, modular monolith is also the same thing. It is assembly of loosely coupled services. The difference between modular monolith is that the communication mechanism is different because they are not independent. It's still part of the same service. And there is this myth, or there is a very common problem in the industry that everybody follows a trend. So everybody's like, let's use microservices for doing everything. Like anything, microservices have their own drawbacks. In fact, there was a famous Amazon case study where they basically changed their microservices to monolith, and they saw a huge improvement in their resource usage. Their resource usage was less, production outages were less. The problem with microservices is that when you have a system that consists of too many parts talking to each other, it's a brittle system. The more number of parts there is, the more things can break. Modular monolith basically kind of solves the same problem. The reason why you want to do microservices is you want independent services with different heterogeneous technologies that can evolve fast. But not everything needs that. For example, in a lot of case studies, I was talking to a friend of mine who worked at a company called WeWork, and we were talking about scalability. He said, you guys face a different scalability problem than us. We don't really have a scalability problem, right? So for us, a monolith just works fine, right? And also the thing with microservices is because you have a lot of services, you need a lot of investment in automation, whereas in monolith, you really don't. In fact, generally for most of the organizations who are building services from scratch, it's often a good idea to start with monolith and then move to microservices. A lot of people just start with microservices, and in most cases, that's generally not a good idea. So in microservices, we have contracts, right? I think the previous speaker also talked a little bit about contracts. Essentially, it's a format that we can use to convey information. And we have different kind of contracts. So we want to do strict contracts, like we have a fixed JSON, schema, XML speaker, RPC, protoboro. Now, evolutionary architecture states that rather than having a strict schema, you should have basically a loose schema. So move from strict schema to a loose schema. What is a loose schema? Loose schema is a one that can evolve. For example, let's say my services is providing some additional fields in my JSON. You can have something like a tolerant reader that parses that schema, but may not really use all that information. It can discard certain information rather than throwing an error. You can also have something like key value pairs. A service is sending me a key value pairs. I can essentially just extract the keys I need and ignore the keys that I don't need. And the reason why loose contracts are better is because with loose contracts, you have more freedom to evolve. So now that we have understood contracts, let's talk about communication patterns. In a loosely coupled systems, there is often a pattern of using asynchronous communication, usually through a message bus, Kafka, or etc. So, and I'll explain a little bit on that, but essentially, before that, I'll talk about that you can generally put your services in three categories: the customer-facing, right, impacting customers, and little to no impact. For example, let's talk about something like Amazon.com, which is an e-business. You have the customer service, the ones the customer directly interacts from. Typically, they are request response, and I'll explain in a bit why they are request response. And generally, what we want to do from an evolutionary point of view is we want to keep the tier 2 and tier 3 as event-driven asynchronous, because it's very easy for us to incorporate new use case scenarios in an event-driven asynchronous architecture. Examples of tier 1 service, you have Amazon.com, you're interacting with the order placement service. That's a tier 1 service. If that service is down, you can't place orders. Your system is down, customer gets impacted. Shipping service is an example of tier 2 service. Shipping service is down, well, your packages may be delayed by a couple of hours, couple of days. It does impact you, but it doesn't make the system unusable. And then you will have your internal auditing, monitoring. Customer doesn't care whether you monitor your system or not. So that's an example of tier 3. Generally, what we want to do is for request response, tier 1, we actually tend to use request response. As much as possible, from an evolutionary point of view, we want to minimize this. The reason why we do it is because it has a very good error control and it's easy to implement. Error control is the main reason why we want to do it, because remember, if these services are down, then the system is unusable. But the drawbacks are that when you have these services, there's a lot of coupling. If you change one component, you'll actually have to change all the components that are interacting with that component. And that makes these services, synchronous services, difficult to scale. So we keep them minimum, and we move as much as possible to what we call as event-driven services, where you have asynchronous messaging. These are easy to scale, easier to scale. They decrease decoupling. So you can add and subtract new services. You can basically add more use case scenarios that you haven't thought about. So these services tend to be a lot more evolvable. Of course, they have a drawback that there's a poor error control because, asynchronous, you send a message, the other person received it, didn't receive it, nobody knows, there is no traceability. To solve these problems, we have tools that do distributed tracing, Jaeger, and there are a lot of open source tools that do that. So now we are talking about event sourcing. What is event sourcing? Event sourcing says that instead of storing your system as a state, you model your state changes as sequence of events. Events that happen in time, events that are immutable. And you just store all the events that, that trigger a state change, and that enables you to roll back in point of time, do an auditing, etc. And the reason why it's a good idea to do event sourcing, not in all cases it may not be practical, is because it enables you to create future workflows that you have not anticipated. In fact, event sourcing is hardly a new idea. In some form or another, it has been there for centuries. Because really, when you look at your bank ledger, it's event sourcing. What is a bank ledger? You open an account, your state, which is the amount of money in your account, is zero. Then you do transactions. You deposit some money, you withdraw some money. Banks keeps a record of all those transactions, and sum these transactions together, you have the total amount in your account. And in case you're using credit card and your credit card is stolen and somebody is using it fraudulent, you call up the bank can roll back in time, it can fix that one transaction and replay that event. So it enables the bank to create a new workflow or change an existing state very easily. If the bank just keeps the state, it's very hard for bank to go back and roll back in time. Version control that we all developers use, that's another example of event sourcing, because every change in the code is a delta, so it's an event that a developer does, and your state of the system, which is your current source code, is nothing but a sums of all the deltas. Event sourcing allows you to create multiple views from the same system. So here is an example of Facebook, right? You have an event. Let's say you got married, and you have in typical Facebook, you have 3 sections. You have photo section, timeline section, your personal information section. The same event is interpreted differently. The photo section will ignore unless you actually post some photos of the wedding. Your timeline would say, oh, Nikhil got married on that day. Your personal information gets updated. When you post some photographs, the photograph section and timeline sections get updated, personal information stays the same way. So when you have event sourcing, you can create multiple views of how, when the events happen, and that again lets your system evolve better over time. So essentially the whole idea is that we are trying to design a system where we don't know what the end state is, we don't know how the system would evolve, so we keep the system open that we can make changes. And all of these architectural patterns essentially are there to support that end goal. Another related pattern is command query responsibility segregation. What is command and query responsibility sections? Essentially, textbook definition is that you have 2 types of requests. You have a read, which basically reads the state of the system but doesn't modify, and you have a write, which essentially will just modify the state of the system but doesn't actually give you any information. And the reason why you have is because when you have event source systems, how do I query that system? That's a big challenge. So CQRS is essentially a pattern that is must for event sourcing. What you basically have is you create, as events go by through your message bus, you create a read model, and read model can read that message. Now, I should point out here that CQRS is an eventually consistent system. So in technical terms of distributed systems, your state is not always the current because it takes time for the write and to process through the message queue and update the read model. But in real life, that usually you're talking about milliseconds update, so it may not matter that much. But again, bear in mind that this is an eventually consistent system. And then you have another problem of sagas and rollback transactions. When you have a large system, a distributed system where you have a long-running transactions, how do I handle that? So in long-running transactions, how we do it is, because the problem with distributed systems often is that we have a concept of partial failure, right? You have a microservice architecture, even otherwise you have 1,000 components running. You could have a state where 10 components fail, or even 1 component fail, the remaining 999 work. Right? So you want to be able to essentially deal with these scenarios in a graceful manner. In a standard monolith, good old days when you didn't have distributed systems, your system is working or it's not working. There is no such concept as partial failure. Now, let's talk about an example of Netflix. Suppose Netflix is running on microservices architecture, different services do different. Let's say one of the recommendation services goes down. You could still use Netflix. You just won't see recommendations. And the way Netflix is designed and the way systems should be designed is it incorporates the facts that systems can partially fail, and if you can operate or you can shut down gracefully, or at least you can have a mechanism to error handle. So if the recommendation service goes down, I can still watch movies, I can still do whatever I want, I just won't have recommendations available to me. That's about it. In sagas, you basically have, sagas is essentially a mechanism where you have a sequence of events and something fails. For example, you have a transaction that was supposed to go T2 to T3, and it so happens that this transaction failed. So the saga mechanism says that every transaction would have a rollback mechanism. So you have a rollback transactions, the T2 has an inverse and goes R1. Where is this useful? A common example is banking. In banking, let's say I want to transfer you 100 euros. So the sequence of action starts, 100 euros gets deducted from my account, and they were supposed to go to your account. It so happens that you close your account. Now what happens? 100 euros is out of my account, but you never got it. So what would the bank do? They will credit the 100 euros back in my account. That's an inverse action of the original action of taking 100 euros out of my account. Now, of course, there are border and edge cases, but if I also close the account, then what happens? Then bank probably will just mail me a check. But in real life system architects, how they design these systems, these different systems that operate, is that they have these long-running transactions, and they basically have a mechanism of how to handle failures and gracefully shut down or do the appropriate actions. Now, so far we have talked about the compute part of it. Let's actually move to data. And data is very important because often data outlives the application. So we have talked about how we can apply evolutionary principles, agile philosophies to software architectures, but how do we do it for data? Same stuff, rigorously test the data schemas. We want to make sure it's stability. We also want to version. Typically, versioning is major versioning, minor versioning. If you're doing a backward, if you're adding, let's say to your contracts, you're adding some fields which is compatible, you're not fundamentally changing, you can do a minor upgrade. It doesn't really require changes to the incoming reader. The service stays the same. But if you're doing a completely different, if you're changing the schema, that's a major one. So that's why you want to have some kind of versioning. Versioning would allow you to handle, because in typical, say, microservices architecture, different services operate, and you have like a gradual deployment. So some services might be running old code, some services might be running new code. You want to incorporate these services, you want to make sure they can handle different types of data. So you version them, they will have like, oh, version 1 of the data, this is what I expect. Version 2 of the data, this is how I expect things. Sometimes you want to have a duplicate data for decoupling, because joins are very expensive, especially if you're using SQL ones. But you also have to understand that these kinds of problems will give you consistency issues, especially in a very distributed systems where you are optimizing for availability and partition tolerance, and your system is eventually consistent. You can run into consistent issues, and you should have a mechanism to handle that. One thing that is generally not a good idea to do from an evolutionary architecture point of view is to have stored procedures, because they are very hard to test and refactor. As much as possible, do everything in the code. And ensure that there's a consistency, there's a referential integrity. You should not have like, products deducted from the product database and customer doesn't receive it. You don't really want to have all of those. And mentioned before, data schemas outlive the applications. Data is going to stay with you for a very long time. Applications, they'll be rewritten in a couple of years. So in many ways, data is often more important than application. The quote, the data is the new oil. Especially in AI world, come on, data is pretty much everything these days. Now we are talking about microservices, so we also want to talk a little bit about architecture principles in microservices from an evolutionary point of view. So generally, it's not a good idea to have more than one database per service. Now, Mind you that when I say database, these could be logical, these could be physical. They may not necessarily be the same actual different instances of physical. They can still be the same physical database, but the tables, the logical separation should be there. In fact, I should rather rephrase it and say the data schemas should not be shared across the services, because the moment you start sharing the data schemas, you're increasing the coupling. If I basically change a schema, now I have to change multiple services, and imagine if I have large number of services running, and some of these services, because when you're releasing, you have gradual deployment. Some of the services may be running old code. Some of the services might be running your code. It's going to be a mess. So you really want to avoid that. In fact, that was a cause of outage that happened in Google. That was 2018 or 19. I remember I was actually working for Google at that time, and they had such a big outage that we had something called reliability reset, whereas the SVP at that time of infrastructure said, just stop doing whatever you're doing. There is going to be no future work, no new features. We all will just pause on all the new features, and what we are going to do is just worry about reliability for an entire 6 months. Because the outage was so big that I don't know how much money Google lost and how many customers basically decided to leave Google Cloud for good. I don't have that statistics, but it sounded like it was pretty bad. And it wasn't exactly said that, but it had something to do with they were sharing this schemas and protobufs and something across services, and some services were running old code that crashed, certain zones went out. So we want to have loosely coupled services. The reason why we want to have loosely coupled services, it reduces the team dependencies and that greater evolvability, which is our North Star here. We'll talk a little bit about Conway's law. I'm running out of time, so I'll go a little fast, but Conway's law, organizations, your communication structures are basically, in organization defines your architecture. So if you have 4 teams working on a compiler, you'll have a 4-pass compiler. The inverse is structure your team such a way that it looks like target architecture. So your organization design basically has to adapt to your software architecture. Towards the end, I actually want to talk about some of the best practices. I've grouped them in multiple categories. These are specifically from an evolutionary architecture point of view. Take reversible decisions as much as possible, because you want the flexibility to evolve as much as you want. Obsess about the solution, not the problem. This is a very common reason why startups fail. They basically solve problems that is nobody's problem. So you always want to worry about, this is something that you don't want to do. You should solve problem. It's actually negative. Prefer evolvable over predictable. Fundamentally, you cannot predict. So what you do is you basically take into the fact that whatever I'm going to do, my solution might change over time. So prefer evolvable over predictable. Don't do excessive customizations. Basically, when you try to please everybody, you will end up pleasing nobody. Culture of experimentation. We don't know what the future is. Lean startup, lean philosophy, agile, they all talk about agile is all about failing fast. Do something, learn from it, adapt it in the next cycle. If you have to fail, that's okay. Failure is part of life. Fail fast. In fact, agile philosophy equal to fail fast. Simple. So this is about feature selection. Now let's actually talk about design decisions. Don't over-architect your system. Architecture is a fancy word. We'll take this into account, that into account. Really, it's not really a good idea. You have a problem, you have a well-defined problem, just focus on the simplest solution for that. Prototyping as a way to know unknown unknowns. Now you have you have some problems that you know the solution. You have some problems that you don't know the solution, but at least you know you have a problem. And then you don't even know some problems in certain scenarios, because when you're developing something, you really don't know what kind of problems I'll anticipate. So when you start, these are the unknown unknowns. So often how you do it is you kind of prototype. Defer decisions till you can. Don't make decisions until you really have to. But then when you really have to, do it. Avoid leaky abstractions. Leaky abstractions is where one layer exposes the implementation details to another layer. You want to avoid them. Make things immutable as much as possible. That's basically the fundamental notion of functional programming. We'll talk about some best practices for technology choices. Prefer libraries over frameworks where possible. And the reason is that frameworks are often opinionated framework. They force you to do things in a certain way which may not be the best for your particular problem. Libraries, in some sense, are a lot more flexible. If you are using frameworks, sometimes you have to, because you want to use something like web framework, Spring Boot, ASP.NET, whatever, update the framework dependencies very aggressively, but libraries, you can do it a little passively. Be very careful with low-code, no-code tools, because what happens is that they make your life very easy for the first 50, 60, 70% of your code. But for the last 30% where you need specialized functionality, they completely fail. So basically at that point, very many times people just abandon the low-code tools and they have to re-architect. Low-code, no-code tool works only when you're only dealing with major cases and you're not really talking about edge cases, so on. Multiple governance model, essentially how you define the software, how you deprecate it, how you use it, etc. You can't really have one governance model for everything. So you basically have use cases like certain test cases, I'll have one governance model. My implementation language choices, I have another governance model. 2 or 3 different governance model rather than having one. And whenever you're using third-party dependency is very careful because you can get into dependent trees and then you're going to have a hell lot of time resolving these dependencies. Sometimes what I do is that if I just want 1 or 2 functions, I won't actually import the whole library. I'll just copy the code and use it. Now, I'm not a lawyer, so I can't speak for the licensing aspect of it, but you get the point. Evolvability, version services, version data, internal versioning. Architect for testability, you want to design systems in such a way that you should be able to test it easily. Anti-corruption layer should be there. You should have fault tolerance. We have talked about tolerant readers. Be conservative in sending, send as little as possible. But on the receiving end, if you have some extra fields, you could do that. Use versioning. When you're breaking contracts, you want to have multiple versioning, so that way you can evolve easily. And I have few minutes remaining. I don't know how many, but I'm up for questions. Any questions?
Okay, thank you very much. Unfortunately, we're out of time, but if someone wants to ask something really quick.
Otherwise, I'm roaming around, so you can always catch hold of me.
Yes, yes, okay. Thank you very much.
Thank you.